Now, in this session, I'm going to be demonstrating how you use a microwave and a large bar of chocolate to calculate the speed of light. Of course, what you're calculating is not exactly the speed of light, it's the speed of microwaves. But as we'll see, these all have exactly the same speed, all electromagnetic waves, and so it should turn out that you calculate that the speed of the waves is about 3 by 10 to the 8 meters per second. But two pieces of advice if you do this as a demonstration for classes, and it's a great demonstration, they love it, particularly because it involves chocolate. But two things you really want to do first. You want to check, and you need to be able to cheat if necessary, because it doesn't always work exactly like you think it's going to. Now, the idea is that inside the microwave there's a thing called a klystron that's an emitter of microwaves, and that the inside of the oven is basically what they call a resonant cavity, so that the waves bounce back and forth, you get standing waves. Now, you know that when you get standing waves, the distance between antinodes is meant to be half a wavelength. But I've found in practice that doesn't always work. So what I've done before even starting to do this, I've checked on the back, and I think all of them have the same frequency, but they'll all have it written somewhere, either on the back or down the inside of the door. It will say, it might be down here, it'll say that the frequency is 2.45 gigahertz. So I know that. I use my equation that frequency times wavelength equals speed of light, and therefore the wavelength should be speed of light divided by that 2.45 by 10 to the 9. What that gives is that the wavelength should be about 12.2 centimeters. Now, I've done this with other microwaves, and I got the distance between antinodes was about 6 centimeters. So that gave the right wavelength. But I've done it with this microwave before, and I was actually getting about 12 centimeters between antinodes. And so that suggests it doesn't make a perfect standing wave pattern. In fact, if you look up on the internet, you'll find pictures where people have put paper that light up where it's hot, and so it shows the pattern of where the hot spots are, and it's not a perfect rectangular grid. So I'm going to try it here. We'll have a look at what you get. I've been told it's actually best to put the chocolate near one side of the cavity, and in particular away from the klystron, but I actually cannot tell which side the klystron is on. So I'm just going to put it down this side and see what happens. So the way it works, of course, is that if we've got standing waves, then we've got antinodes, and that is where the electric field and magnetic field are at a maximum. And so that is the spot where the atoms in the chocolate are going to get made to vibrate a maximum amount. So these are the spots that heat up. And the trick is to not run the microwave very long. So what I've done, and this only works with the turntable ones. If it's one where you've got the food sitting still and the microwaves getting circulated from fan blades that reflect them, I don't think this will work. But if you've got a turntable, then what you do is take the turntable out, which I've done there. Then you get something like a plate or a bowl, and you put it upside down so that this thing that turns around is not going to make this plate turn, because you want it to sit still. So I put it in there. I'm going to try it with the chocolate down this side, because when I got the wrong result before, I was putting it in the center. So I'll put it there. I've got it on high, and I'll go for about 10-second intervals, because it really doesn't take long for this to work. So I will start it with, I'll time it myself. Now, if you're doing this stopping and starting, don't move it between intervals. Okay, nothing yet. Here we go. And in even that short amount of time, I've got two very obvious antinodes. If I hold it up, you can see here two spots where it has melted. And when I look at the distance between them, oddly enough, there's nothing else over the rest of the chocolate. But it's about 10 centimeters. So in fact, given that we expect a wavelength of about 12, I think this is the point where you would carefully measure it yourself and say, yes, that distance is 12 centimeters, so let's take our wavelength is 12 centimeters. So as I said, sometimes you need to cheat a little bit to get this to work effectively. But very popular with the kids. If we did that, if we assumed that our wavelength was 12 centimeters, we'd then plug that in. So we'd say 0.12 meters times our 2.45 by 10 to the 9 hertz, and that gives us 2.94 by 10 to the 8 meters per second. So you see, the kids should be able to calculate for themselves and get something pretty close to the speed of light if you've guided them with approximately the right numbers.